All right, in this section, we are going to be revisiting inverse trig. So I have a lot of it summarized here for you on this first page, and we'll go through it. And as you can see, there's also some resources in your book for this inverse trig as well. So if you did check out a book and you have it at home, or you're using that PDF from Safari Montage, there's some extra resources. So the first thing that I want to point out is the different notation. Notice this says arc sign. Last year in pre-calc, I used the sign inverse notation. That's a 1. These two different notations are identical. They mean the same thing. Your calculus book uses the arc notation, so I want to use that as well so you get familiar with it. But drawing your attention to that connection from last year, arc sign and sine inverse are the exact same function. So what it does is undoes the sine function. As a reminder, for our regular trig functions, the input is the angle and the output is a ratio. So that flips, the domain and the range flip when we're talking about the arc function or the inverse function. So the input for the arc function is a ratio and the output is an angle. The domains and range switch. So the range of the sine function is -1 to 1. Think about that wave when we graphed the sine function, or even the unit circle. The biggest sine value is 1, and the smallest sine value is -1. So the range for the arcsine function is -π/2 to π/2. Now, the sine function has a domain of all real numbers, but as a reminder, we talked about these inverse functions also need to be a function. So the sine function fails the horizontal line test. So what we do is we just cut a chunk of the graph that covers all of the values from -1 to 1 and passes the horizontal line test. And so this is that chunk of the domain that we use, so it becomes the range for that arc function. When you look all the way down at the bottom underneath those trig functions, these three have a range that's a half moon. Now the fourth quadrant values that the arc sign gives us are not like 11π/6, because then the part of the domain that we cut wouldn't be continuous. So you have to think about the angle rotating backwards to -π/2 and then rotating forwards to π/2. So that's what gives us that like half moon range for these three inverse functions or arc functions. All right, I would go through all of the rest of these, but 1, you all know how to read, and 2, I don't think you want to see a 40-minute video from me. So take a moment, pause the video, take a look through these other trig functions. Although one more thing that I do want to point out is this half sun. So real quickly, let me get rid of what we were just talking about with that half moon and talk about the half sun. So think about when you see the sun coming up on the horizon, right? If you see about half of the sun, it would be a semicircle above the x-axis, so to speak. And because I don't think I did a great job explaining that half moon, when the moon is half full in the night sky, you would see it on the right or the left-hand side. So that's what those notations are designed to help you remember. If we weren't distance learning, my plan for this example was to break you up into groups and have each of you study the graph of the 6 different arc functions. The one that we were going to focus on a little bit more than the other ones is the arctan function. I'm just going to sketch a quick graph of that for you below. Actually, before I do that, as a reminder of what the tangent function looks like, we would have asymptotes at π/2 and -π/2. And what the tangent function, again, this is the tangent function, what the tangent function looks like a cubic function. So thinking about flipping that across the y equals x axis, the arctan function would have horizontal asymptotes at π/2 and -π/2, And it's kind of like this exact blue function, only sideways. So this purple graph would be the arctan function. Evaluating this will give us some great practice for remembering our unit circle values. So that's the first thing that I'm going to do is set up a little unit circle here. I'm a visual person, so I like to see what's going on. I'm thinking about where is my sine value equal to 1/2. We're really used to thinking about this angle goes into the sine function and I get this ratio out of it. So I'm going to still think that way. Sine goes 1, 2, 3 because sine is the y value. So it starts small and gets bigger as you go. So my arc sine of 1/2 would give me that smaller angle, which is pi over 6. All right, the next one is a little bit more challenging because we don't memorize the tangent function values as easily as we memorize sine and cosine. First of all, it's not a counting order. It's not 1, 2, 3 or 3, 2, 1. It would be very helpful if you do memorize the tangent values. It's root 3 over 3 at pi over 6, 1 at pi over 4, and root 3 at pi over 3. What's nice is that the cotangent function flips those. Well, the reciprocal of 1 is still 1, and these two are reciprocals of each other. So for our cotangent function, we would have root 3 at pi over 6 and root 3 over 3 at pi over 3. So the arc cotangent of negative root 3, our cotangent is a half sun. So we have to think in the second quadrant. So first of all, my reference angle is pi over 6. In the second quadrant, that would be 5 pi over 6. My last one, negative 3/5 is not a value on the unit circle for my tangent. So what I'm going to do is think back to Pythagorean theorem, and I'm going to set up a triangle. Now this is arctan of a negative. Tangent is half moon, so this will be in the fourth quadrant. So this is the origin. This is supposed to be the x-axis. Notice how nice and straight my line is. And then this is the angle that is our reference angle. All right, so in the fourth quadrant, the x value is positive and the y value is negative. So tangent is opposite over adjacent. And then what I would do is use Pythagorean theorem to solve for the missing side. Since I know you all are very familiar with Pythagorean theorem, I'm not going to cover that in the video. The hypotenuse is square root of 34. All right, so secant of that angle. Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So secant is hypotenuse, square root of 34, over adjacent, which was 5. Example 3a is very similar to example 2c, except for we don't have a number. So our answer will not be a number either, but we're still going to set up that right triangle to help us as a reference picture. All right, so as a reminder, with these arc functions, what goes into the arc function is a ratio. What comes out of it is an angle. So what it's saying is that y is our angle, x, or x over 1, is our ratio. So when I set up this triangle as a reference, y is my angle. Cosine, again, is adjacent over hypotenuse. So my adjacent is x, and my hypotenuse would be 1. Using Pythagorean theorem to solve for that third side, I would have the square root of 1 squared minus x squared. All right, so now I'm looking for the tangent of y. Well, tangent is opposite over adjacent. So tangent of my angle is opposite square root of 1 minus x squared, all over adjacent, which is x. At first glance, this equation might not look doable, but what we're going to do is cancel either the arc cosine or the arc secant. Since we're more familiar with the cosine function than the secant function, I'm going to take the cosine of both sides. As a reminder, arc cosine and cosine are inverse functions, so they are going to undo each other. Once we do that, we're just going to set up the triangle like we have been to solve for the cosine of the arcsecant of x. All right, so that's what x will equal. Again, the input of an arc function is a ratio, and the output is an angle. I'm just going to use theta as a reference angle again. Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant would be hypotenuse over adjacent. Now, what's the cosine of theta? Well, that would be 1 over x. So what we have is x equals 1 over x. And I apologize that all of my equal signs end up looking like z's. Now we need to solve this equation for x. So I'm going to multiply both sides by x, and then take the square root of both sides. I wanted to jump back to this page because I'm sure not all of you have the domain for arcsecant memorized. Notice it says the absolute value of x has to be greater than or equal to 1. That means we can put 1 and bigger into our arcsecant function, along with -1 or smaller. So both of these answers that we got on this problem, positive and -1, both fit into the domain of the arcsecant function, so they are both possibilities.